Welcome to another teardown video. Look at this instrument. A Philips PM5711 pulse generator. It's amazing how well this looks. I mean, this is designed in the 70s, so it could be up to 50 years old. Amazing. So here's what it can do. This is the pulse width, and then you have a variable for the pulse width. This is the signal level, how much you want. Of course, you can invert the output. I don't understand about this delay. I think we're going to understand when we power it up and we test it. Here is the repeat. So this is in time. So you can say every 1 millisecond. If this is in 1, this is in 3. Oh, that's funny. So that means what? Where's 1? Okay, here. So this is 1. So that means now we have 1 millisecond, I guess. Right, and what? And then 100. And then, okay, so that means 100, I guess. We're going to figure this out. So external triggers, and then you can select if you're running on internal, on external trigger, or external AC. So if it's AC or DC coupled, that's a little bit funny. And then the level for the triggering, this is the input for that. So there's a pre-pulse. Maybe this is for a trigger of a scope. So maybe this happens a little bit before the real pulse. Or maybe this is the trigger input, or the, I don't know really what that is. The instrument is really big compared to today's standards, especially the height. I really like the carrying handle. See, it's either down or up, but if you want to carry the unit, it's just really nice. Nice chrome. Fantastic. You can see, ooh, I can also smell. I can smell the age. And there was another funny thing I really wanted to show here. Look at the mains input and mains output. So that means if you have a lot of instruments stacked up on a shelf, what you do is just daisy chain the inputs, outputs, and this way you have a nice clean lab without all those cables flying around in a one big nightmare like we have today. So back in the 70s, they already knew about cables and craziness in the lab. Look at that earth connection. Just big, bad and solid. So, and I also measured this earth is 0 ohms to that and to this one, and of course there's a direct connection between these two and those two, so there's direct feed through even if the unit is off, so you can turn on other instruments without this being on. And it's set for 230 volts, so that means it is test time. Is this luck or brains? You never know. What if this was the other way around? All right, I guess it's brains. Okay, let's. Mains is applied, and I read 0 watts. So far, so good. Are we ready? Ooh. No kaboom. No light. 26 watts. And no light. 26 watts almost, huh? So maybe it's just a... Is this a lamp or a neon? I don't know. Let's try and... Oi! Look at that! Yeah. Oh, this pot is like scratchy. But let's look at that. This is... We got a pulse. And the... Ooh. So the pulse is negative. Oh, it's negative. I didn't expect that, because this is positive. If I flip this... Oh, that is funny. So... what? Okay, this is the positive. This is the pulse. Right? Smaller pulse. Okay, so now this is the pulse. Ah, confusing. Okay. 10 microseconds, 10, and then 1. I would expect this to be 10 microseconds, the pulse. Okay? And what is that? Look at that. 20 microseconds per division, and this is half a division. What if I turn it like this? 10 microseconds. Isn't that crazy? This thing is accurate. What the heck? And this is the repeat. So now we got 50 microseconds per division. So let's see about this. So, aha. So this is 100. And I don't know. I really don't understand this. So this is clearly the repeat and all that. What is this? This is scratchy. So this is the funky effects button where you can make. This is absolutely fantastic effects. I don't know what you can use that for, but I haven't figured out where we have the 100. So cal, but it says 3. Eh? How is that possible? So I put it for 3, and then what? So that is aha! 100 microseconds, and then 3 of them. A little bit more maybe. So okay, so that is what it is. So if this is 3, 2, and 1. So that should be 100. So now that is 100 and a little bit more. Here is 100. Okay, so it's not super accurate. Okay, isn't this quite alright? So what is this? Aha, this is the external trigger input. Maybe we should try and play with that as well. But as far as I can see, we got really nice pulses going out. And it's variable. Ooh, and then it goes. Okay, so you can't put this pot all the way down to 0. Then it's gonna go crazy. But so far, so good. Let's try the shortest possible. That is 1 microsecond. And here it should be 1. Right? So let's try and dial in. Is this? Yeah. That is 1 microsecond. Somebody needs to clean the scope. How annoying is this? Okay, so 1 microsecond. It's really, really accurate. Wow. So if this is 1, how small can it really do? Half? Ooh. Look at that. 100 nanoseconds. Yeah, and then it goes. So you can even make a 100 nanosecond pulse, and the rise time is absolutely amazing. Now I'm trying to give some more voltage. We can maybe try and get this down here and then crank it up. play with this. Yeah, see, this is how it looks better. Give it some more. Ui, ui, ui. Look at that. Oh, that was the full. Okay, that is the problem. Ooh, we can get a lot of signals, and this is in... Are we in 50 ohm? Yes, we are. And in 50 ohms, of course, we go like this. So now it should be accurate. And just take it out of the scale here. And remember, this is in a 50 ohm load, and this unit is from 1970. Look at that! This is a 100 nanosecond pulse. This is really, really great. And the rise time is really, really amazing. Maybe we should try and measure that as well. So it was that simple. I just added measurements. So the rise time and the fall time is here. I think this is pretty amazing when we compare how old this unit is. But enough of this playing around. Let's open. Before we open, I need to show you this, because now the power usage is only 16 watts. So how is that possible? Let's try and turn this off, and it goes to 0. And then if I turn it on again, 16 watts again. So something is a little bit weird. I think this is one of my first time into an instrument like this. But look at this. This one is not a screw, but it is like a locking mechanism. You kind of lock or turn, and then you should, I don't know, kind of lock it like this, and then maybe, yeah, okay, so you pull it. Really, really weird. So how is that designed? Okay, so there's a flat locking thingy. Look at that. So it goes into here. Maybe, aha, you just press it in and then it goes clickety click into this sharp locking. Wow, they're thinking about everything. Wow, look at all that. What is that? This is really, really beautiful. Okay, the power lamp is indeed a lamp. Down there is the power lamp. This one looks a lot like a lamp, and I'm sure if you, yes, this is how you undo that one. Okay, I need to find some proper tools. Then I should be able to pull this out and replace the bulb. Or maybe just measure if there's voltage on the bulb. The wires here, it's all tied up, really nice and beautiful. And that will be all the timing components and the attenuator components. Look at that, 0.5% on those resistors, right? Or 1.0.5. That is a little bit weird. I don't know. But at least that looks pretty beautiful. And here we got the repeat timing components. Again, on some really fascinating switches. And big capacitors here on the back. Remember, this is a 16 watt unit, and look at this amazing piece of heat sink. This must be like power supply components and more. I guess this is the repeat board, and then there's an output pulse board and a power supply board. Yes, exactly. I think we should try and take off the sides, get some more light in here and have a look. And this is again super genius design. So you take off the handle, only one screw, then you lift up. And then you pull, and then you're in. Isn't this just beautiful thinking? So now we are in. I like this. This is like really old tech. Germanium transistors. Isn't this just fantastic? Do you guys remember those from the good old times? And look at all those trimmers and this beautiful red plastic. Oh, so this is, yeah, that is what I thought. Some sort of a cover. It looks a little bit loosey. Ooh, look at this coil. You can also trim the coil. The power resistor down here. So the whole pulse output system is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 transistors. That is it. This is in the entire pulse output. 10 active components, and the power supply is like 1, 2, 3, 4, 5, 6, 7, 8, 9 maybe transistors. That's it. And then again, this is the repeat board. Oh, let's open and have a look in the repeat board. Ooh, look at that, even more trimmers. A little coil here. Big, beautiful capacitors. And only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 transistors. What is that doing? That is a switch on the back. Oops. Yeah, okay. Voltage selection. So you loosen the screw and pull this up and down. Okay. Pretty cool. So this is an up and down voltage selector. Oh, is this really mains voltage in those thingy wires? All the way here, and then this is for the feeding through as well to the other side. I hope you don't put anything bad on the, yes it is indeed. Those are the thin wires to the next instrument, but of course I would expect all the instruments to be using very little power. So, and obviously, if you read the manual, it will say something about don't load the output more than, I don't know how many amps. Not that many, I would guess. But yeah, it's mechanically really well engineered, and all this is really thick and stable metal parts. And the transformator is really big and heavy, and of course this was designed in the time right after tubes, so stuff needed a certain size and weight to be anything good, because this one could have been made a lot more compact. But that is not the thing. stuff was not supposed to be compact. It was supposed to be this size. Yeah. And this is a little germanium diode. Beautiful. Yeah, I don't think I will poke around anymore in this beautiful unit. I will just put it all back together and hopefully trade it for something more fun to disassemble.